Hello, human mathematicians. Welcome to the second part of the discrete unit. We'll still be counting, but we'll shift our focus to sequences and series. In this lesson, we'll focus on infinite sequences. Before I teach you some stuff, I need to motivate you. There's a sequence here, 7, 10, 13, 16. I would like you to find the 100th term of this sequence. Do it as fast as you can, but can you do it in 3 minutes or less? Pause now. If you did this, that's great. You're counting. That's the whole idea of this unit. And you go to the 100th term, and you'll find that term. But some of you did this. You know that 7 is the first term, and you know you had to take 99 steps to get to the 100th term. But some of you might have said, well, I know if I start at 16 and continue, I already took 1, 2, 3 steps, so therefore I need to take 96 more. You'll still end up with the same answer. That's what we'll be doing in this topic, kind of counting and finding out the terms of a sequence. We can categorize sequences in a few different ways, but before we write anything down related to that, I want you to know that from now until the end of the school year, the motivation for our studies is to learn pure math and to prepare for calculus. Even though we're studying discrete math right now, it helps us understand calculus concepts, like the idea of a limit. It's a really big idea in calculus. So if you're planning on taking calculus next year, anything that we do in this topic and the next topic related to limits, you should pay attention to. So what's a sequence? Well, a sequence really is just a list of numbers, a progression of numbers. So you could write that down next to the word sequences in your notes. Like I wrote there, that progression could be finite or infinite, and you could write that down, but just know that finite means we have a fixed number of terms, and we don't care so much about that right now, especially as we approach calculus concepts. But we do care about that in general in math. And then an infinite sequence is simply a sequence that has an infinite number of terms. It just never ends, just like the number line. Our focus in this lesson is on infinite sequences. Let's talk about explicitly defined sequences first. And that begs the question, what does explicit mean? Well, in music lyrics, explicit means you don't have to wonder about what the word is that the artist is saying. In math, explicit means that there's a formula to find out what you're looking for. There's a formula for the sequence that we could use to calculate the terms. And implicit would mean that we just don't have the formula, that it's implied. So kind of like in the previous slide, we had a list of numbers, and it's implied that the next term is going to be the previous term added to 3. But in everyday life, we can imply something but not actually say it. So we don't have an actual formulaic word to say what we're saying. We're just saying it with our body language. Okay, so you should have some space to write this example and work it out with me. The example is this, that we have a formula, u sub n equals n plus 1 over n. And we could say b sub n or z sub n or m sub n, whatever. But n we use as a subscript because n is the number of the term. And that formula is n plus 1 over n. So we're going to find the first 6 terms and the 100th term of this sequence. All of these terms, or any term we're looking for, can be found simply by plugging in the number of the term. So the first term is u sub 1, and we plug that in for the n. So we get 1 plus 1 over n, which is 2. And then let's do u of 2 over here. I don't know, you could just write the actual values. You probably don't need to plug it in. So u sub 2 would be 2 plus 1 over 2, which is 3/2. And then I'm not going to write it for the third term. I'm just going to just do it in my head. So 3 plus 1 is 4 over 3. And then the fourth term I could start to see a pattern now. This is 2 over 1, 3 over 2, 4 over 3, 5 over 4. And then u sub 5 is 6 over 5, 7 over 6. So therefore, u sub 100 is equal to 101 over 100. And those are the first 6 terms and the 100th term. Usually we would just like write that in a list and not use the formula all those different times to figure out what those numbers are. Just write it as a list. The other way that we could define sequences is recursively. So what's your morning routine? What do you do first? Do you take a shower first, brush your teeth, have some food? Or maybe you're like me, you like to gargle with mouthwash first, then you'll eat your food, and then you'll brush your teeth. So what I do second depends on what I do first. What I do third depends on what I do second. A recursively defined sequence is just like that. The next step depends on the previous step, or each term depends on the previous one. So let's work an example together where we're given a recursive formula. So in this example, we're asked to find the first 4 terms and the 8th term of the sequence. So the recursive formula is this. We have to be given the first term, which is 8, and then we're given this formula down below, which at first looks a little complicated, but it's not really. We have a sub n equals, that means the nth term. It's equal to the n minus 1th term, or the n minus 1st term. So whatever n is, you take the previous term, and in this case, we subtract 4. We could also add something, we could also multiply by something, or divide by something. In this case, it's just a basic example where we subtract 4. So the first term, so I'll go like this. I'll do a sub 1 and go across here. And I'm going to go all the way to 8 because, you know, I really need to know 5, 6, and 7 in order to know 8, right? So there we have that. And so the first term is 8. That's given to us. And then we subtract 4. Then we subtract 4 again. And we could keep going negative. You know, there's nothing keeping us from being negative value, to have negative values. Negative 8. And you know, I could have stopped at negative 4 and then done the rest in my head, but I might as well just write it out. Negative 16 for the 7th term, and therefore the 8th term is negative 12. And again, you could also like think about how many steps there are. You know, there are 1, 2, 3, 4 steps between the 4th term and the 8th term, so we're going to subtract 4 times. You could do it that way. The rest of this lesson will focus on limits of sequences. So let's talk about the future. It'd be really helpful to write these sequences down on the left part of the space that you have. So where do you think this sequence is going? We have 2 and then 1, or we could call it 2 over 2, 2 over 3, 1/2, which is the same as 2 over 4, 2 over 5, which really is 2 over n. So the sequence is defined explicitly by 2 over n. Well, if n is approaching infinity, then 2 over n is approaching 0. How about the next one? We have multiples of 9, 9, 18, 27, 36, 45. Well, this really goes forever, right? So the result would be infinity. But we would call this diverges as well. So diverges meaning it goes away from any number that we think it might approach. And infinity is not a real number. How about the next one? We have basically negative 1 raised to the n power. First it's negative, then it's positive, negative, positive, negative, positive. So what we have in this case is negative 1 or 1. But it's not both, and it's not one or the other. Really, it's fluctuating between those two values. So we would call this value diverges as well, because it's not approaching one specific number. Okay, how about with this last one? What happens when n is large for this sequence? Really, this connects to an example that we did earlier, the first example. 2 over 1, 3 over 2, 4 over 3, 5 over 4. If you think about a really large number, we have 1,000,001 divided by 1,000,000. Or 5 billion divided by 4,999,999,999,999. Okay, so the larger the numbers are getting, the less it really matters that they're 1 unit apart. So this approach is 1. Here's a semi-formal definition of limits of sequences. I don't think it's important that you write this down, but listen to me explain the large print here. Let A sub n, which is the formal notation for a sequence, be a sequence of real numbers. Okay, real numbers, got it. And consider the limit as n approaches infinity of that sequence. So thinking about plugging in infinity, but not officially because it's not a real number. It says if the limit is a finite number L, then the sequence converges. In other words, if the result is a real number, then it's a convergent sequence, and L is the limit. But on the other hand, if the limit is infinite or non-existent, like in our case, the actual symbol infinity or 1 or -1, something that's not clear, then we would call that diverges. All right. Let's wrap up this lesson by finding out if these sequences converge or diverge. Again, it's helpful to write these down so you could see some of the patterns emerge. For the first one, this definitely converges, and the mnemonic that I would use is the Betsy mnemonic. When the bottom equals the top, the same power. So 3n and n have the same power. So if we divide 3 by 1, we get 3. That's what the sequence converges to. Now for the next one, I would say that also converges. And in this case, we have a degree that's bigger on the bottom. So that would be a Bobby 0 situation. And that converges to 0. And then for the bottom one, what we have is this is basically equal to n cubed over n squared. And whenever we have a power that's larger in the numerator and we take the limit as the number goes to infinity, what we have is something that approaches infinity. So diverge for that one. All right, so those are the 3 that I did for you. And I would say the only one that's kind of unique here on the right side is that one in the middle. So I want you to try those out and see what you could find. The answers are on the next page. Okay, that's all I have for you. I hope that lesson was straightforward. Talk to you in the next one.